In this tutorial, we use open-source Electrisim to study reactive power and voltage control in a 450 megawatt offshore wind farm. Then verify European network code requirement for generators, grid code compliance at the 400 kilovolt point of connection. The model is free, runs in your browser, and uses Pandapower under the hood. Validated against commercial tools like Power Factory and SyncOwl. We will walk through reactive compensation equipment, run a baseline load flow, then use grid code compliance analysis for P-Q from Network Code Article 21. The required characteristic in the grid connection point is shown at this image, which presents how much reactive power shall be delivered or consumed depending on active power. A follow-up tutorial will cover another characteristic, voltage, reactive power at Pmax. Let's proceed with the model. Open app.electrisim.com. Start from the template gallery. Choose offshore wind farm. 15 megawatt wind turbines connect through a 66 kilovolt inter-array network to the offshore substation. A 100 kilometer, 275 kilovolt export cable links offshore to onshore. The point of connection is the 400 kilovolt switchgear, modeled as the external grid bus. Reactive power and voltage are managed by coordinated components from turbine to grid. Each 15 megawatts full converter turbine is a static generator with a built-in P-Q capability curve. Each turbine step-up transformer is 16.6 MVA, 0.69 to 66 kV, with OLTC on the high voltage side. Inter-array cables use offshore 66 kV line library presets with defined resistance, reactance, and capacitance per kilometer. The offshore substation transformer OLTC controls voltage on the 66 kV side. A fixed shunt reactor compensates export cable charging. Onshore transformers use OLTC at 275 kV and 400 kV. The variable shunt reactor uses a characteristic table with discrete steps versus active power. This is a real study model, roughly 70 buses. Use components data overview to review all parameters. You can also easily edit model parameters through these tables. Let's proceed with first load flow simulation. Click Simulate, then Load Flow. Choose Pandapower tab, Newton-Raphson algorithm. Enable controllers for transformer taps, shunts, and generators. Results show bus voltage coloring, line loading, and tap positions. The Network Health dashboard summarizes network condition. Let's proceed with checking the whole characteristic. Click Simulate and then Grid Code Compliance. Select 400 kV POC bus, external grid, and all WTG static generators. Q mode, from static generator P-Q curve. Include tap and shunt controllers. Set voltage to 1.0 and active power steps 10. Apply proper characteristic. Calculate. Red curve is achieved capability. Blue is grid code requirement. As you can see, the wind farm does not comply with requirements. Let's look at result point of reactive power, which is minus 128 MVAR at the PCC. The active power is 225 megawatts. It was not computed at the generator's full underexcited capability. Each static generator is dispatched at minus 7.25 MVAR equals minus 14.5 times 0.5, i.e. only 50% of its Q absorbing capability. The engine wanted to use the full minus 14.5 MVAR. Tried it first, but the power flow failed to converge, so it backed off down a fixed ladder until it found a fraction that solved, and that was 0.5. So the minus 14.5 MVAR/unit would improve, widen, the underexcited boundary. It simply wasn't usable because the deterministic Newton-Raphson solve diverged there. Follow us on for the next parts of tutorials when we will get the electrical system compliant with grid-coded. Please subscribe to Electrisim software to support open-source software. Thanks for watching.